For this experiment, you will need a compass, insulated wire which is sufficiently flexible to wrap into a coil, so a thin gauge wire is best. In addition to a longer piece, you'll also need a couple shorter pieces, and if you have alligator clips to attach to the end of them, that would be great, but it's not essential. Just about any scrap wire will probably work. You can get some by tearing apart things like old telephone wires, audio cables, or lamp cords. Uninsulated wire, and it's probably best to use heavy gauge. And if you don't have uninsulated wire lying around, you can just peel the insulation off some insulated wire if you need to. You could also use 2 nails if you don't have heavy gauge wire. Probably even 2 metal spoons would work, but the experiment might corrode or discolor the spoons, so don't use good flatware. A transparent cup. It doesn't actually have to be transparent, but it will be easier to see what's going on if it is. A battery. We found a standard 9-volt battery to work well. If you only have smaller batteries, you can use several in a series to get a higher voltage. Table salt. A stirring device, ideally not metal. We used a small wooden dowel from a broken kite. A chopstick would also work well, so save one from your next takeout order. A computer with spreadsheet software. And this is not essential, but sandpaper to polish your non-insulated wires would be helpful. To set up the experiment, first we're going to make our own ammeter. Take 1 to 2 meters of thin insulated wire and strip a little bit of insulation off of each end. Coil the wire tightly around your compass. You may need to use some tape to keep the coil in place. The more loops you do, the more sensitive your meter is going to be. But if you try to use a super long wire so you can make a lot of loops, the extra resistance you're adding with such a long wire will just eliminate any extra sensitivity that you could hope to gain. And you also still want to be able to read your compass, so don't do too many loops. What we've done here in the video is about right. To test the meter, place it on a table and rotate it so that the compass needle is parallel to the coil of wire. Then, very briefly, touch the 2 ends of the wire to opposite terminals of a battery. The instant you make contact, the compass needle should jump to perpendicular to the coil. Remember to only briefly touch the battery. If you hold the wires to the battery terminals for too long, you could drain the battery or hurt the compass or both. Anyway, if your compass needle jumped, then you're good to go. Next, take your cup and make sure it's really clean. Any residue inside could mess up the experiment. Then, take 2 pieces of uninsulated wire, each about 20 centimeters long, and place them inside your cup. A good strategy is to bend each wire like we have so that it clamps itself to the edge of the cup. Make sure that the bit inside the cup reaches almost all the way to the bottom. These wires are going to be your 2 electrodes. Next, add water to the cup until it's mostly full. You want enough water so that a good portion of both electrodes is submerged. Now we'll set up our circuit. Use a length of insulated wire to connect one of the ends of your compass meter to one of the electrodes in your cup. We used wire with alligator clips, but if you don't have that, that's fine. You can just twist the ends of the wire together. Using another length of insulated wire, connect the other end of your compass meter to one of the terminals of your battery. And then take a final piece of insulated wire to connect the other terminal on your battery to the other electrode in your cup. Now your circuit is complete. While you're not running the experiment, you can go ahead and disconnect the battery from the electrode. Again, we don't want to drain the battery. Before you start taking data, adjust the compass so that the needle is parallel to the coil of wire. And then tape down the compass so it doesn't move throughout the experiment. Now that we're ready to start, reconnect the battery to the electrode in the cup. Once you've made the connection, note the deflection in the compass needle. The needle will either not move or only move a little bit. Ours deflected about 6 degrees. If you're getting an appreciable deflection, you either have created a remarkably sensitive meter or you have salty water, and then you should go back and rewash your cup and put clean water in it. But if all looks good, you can disconnect the battery and record the data. Make sure you note both the amount of salt in the water and the deflection of the compass needle. Next, add salt to your water. We added 1/8 teaspoon, but you can add 1/4 or 1/2. Just note that if you add larger amounts, you won't be able to get as many data points. Use your stirring device to stir the water thoroughly. Make sure all the salt is dissolved. When you're done, reconnect the electrode to the battery and note the compass deflection. Remember to record both the amount of salt in the water and the amount of deflection. If your compass needle only deflected a little bit, or even not at all after adding the salt, you can try adding larger amounts like 1/2 teaspoon. Either way, continue adding measured amounts of salt to the water and recording the compass needle deflection until either you cannot dissolve any more salt in the water or the amount of deflection stops increasing. Deflection on our compass meter peaked at 68 degrees. Once you've collected all your data, you can enter into spreadsheet software like Google Sheets or Excel. First, make a column for the quantity of salt in your solution. Then make another column for your compass hand deflection. Finally, select your data and insert a scatter plot. Be sure to give your graph an appropriate title and label your axes. What does your graph mean? What is the trend telling you? To answer these questions, let's look at the theory behind the experiment. The Earth has a magnetic field. Its field lines run roughly north and south. The small magnet of a compass needle aligns parallel to these field lines. That's why a compass needle points north. If there is a magnet nearby, the magnetic field will be a combination of the field due to the Earth and the one due to the magnet, and a compass needle will align parallel to the new magnetic field. If the magnetic field is sufficiently strong, its field will overpower that due to the Earth, and a compass placed nearby will align with the field lines of the strong magnet. In addition to the Earth and your standard bar magnet, a magnet can also be made with an electric current. The flow of current through a material is governed by the presence of charge carriers, both negatively charged and positively charged, and their freedom to move, which is termed their mobility. Neutral particles don't carry charge because they are unaffected by an applied voltage. When current flows through a material, say a wire, a magnetic field is created circling around that wire. You can use the right hand rule to identify such a magnetic field. Just take your right hand and align your thumb along your wire in the direction of current flow. Then curl your fingers around the wire. Your curled fingers represent the magnetic field created by the current flowing through the wire. The same is true for a coil of wire. Just align your thumb in the direction of current flow and curl your fingers around the wire. Again, your curled fingers represent the magnetic field which is created by the current flowing through the wire. Because a coil of wire bunches many sections of a single wire together, the magnetic field created is stronger than for a single wire. And in the center of the coil, all the magnetic field lines get clustered together, creating one super strong magnetic field that points straight through and perpendicular to the center of the coil. This magnetic field is strong enough to overpower the Earth's, so when a compass is placed inside the coil, the needle will align parallel to the new field lines, which point straight through the coil. This allows us to turn our compass into an ammeter, because when only a little bit of current flows through the coil, the magnetic field created is only strong enough to move the compass needle a little bit, compared to when a lot of current flows through the coil, the magnetic field created is able to move the compass needle a lot. So the deflection of the compass needle can actually give us an idea of how much current is flowing through the wire.
To look a little deeper, let's start with Ohm's law from Introductory Electricity and Magnetism. This tells us that the product of the current flowing through the circuit I and the resistance of the circuit R is equal to the applied voltage V. Resistance is an extrinsic property. It depends on the quantity of material. We are interested in intrinsic properties of the material, properties that the material has regardless of how much is present. Instead of using R, we can rewrite the expression in terms of the intrinsic property conductivity, sigma. Here is the relationship between the two. You can see that resistance depends on the length of the path of current flow and the cross-sectional area of the path A. If we substitute this expression for resistance into Ohm's law, we obtain an expression that relates applied voltage and conductivity, which we are going to rearrange to solve for current. Arg, we're running out of space. Let's put that same equation at the top of a new column. We need to make one more substitution. Conductivity sigma depends on two factors, the concentration of charge carriers C and their mobility mu, which is a metric of the ease with which they move around. Substituting for sigma in the previous expression gives this final result. Mobility mu is an intrinsic property and is constant, as long as the temperature is constant. For a given experimental setup, A and L are also constants. Therefore, under constant applied voltage, the current that flows is directly proportional to the concentration of charge carriers. Moreover, if there are no charge carriers, no current will flow. Measuring how much current flows through a solution when a voltage is applied will reveal the presence and concentration of charge carriers, a macroscopic measurement probing atomic scale structure. The action of a compass and coil as an ammeter is easily demonstrated with a 9-volt battery and a few small resistors. We used resistors of 47 ohms, 100 ohms, 240 ohms, 287 ohms, 460 ohms, 560 ohms, and 1009 ohms. By Ohm's law, the current flowing through the wire in the presence of the 100 ohm resistor is 0.9 amps. In the presence of the 240 ohm resistor, it is 0.038 amps. The graph shows the observed deflection of the compass needle as a function of the calculated current using each of the 7 different resistors. You can even use such a curve as an absolute calibration of the meter. If you want to try this and calibrate your own compass meter, you will need an assortment of small resistors like the one shown here. You can probably get what you need by tearing apart some junk electronics and salvaging the resistors. This is not an essential step and more in the realm of something for an electronics hobbyist. You will need to learn how to read the color code stripes on the resistors so you know what the resistance is. Here is the color code. It shows that this is a 1500 ohm resistor. The setup is the same as the setup for the main experiment. You're just going to replace the cup of salt water with a resistor. And then you're going to record the compass deflection for each resistor you have. Then you can graph the data to use as an absolute calibration of your compass meter. In other words, the graph will tell you exactly how much current flows through the wire based on the compass needle deflection. Now let's look back at our graph from the experiment. It's clear that as the amount of salt in the solution increases, the compass needle deflection increases, which we now know means that the amount of current flowing through the wire is also increasing. So salt increases the conductivity of a solution. But why isn't that relationship linear? A search of the web suggests that the most likely possibility is that the ions are so strongly bound to their solvation shells that they are effectively sodium-water clusters and chloride-water clusters. These clusters are much larger than the isolated ions. When the solution becomes highly concentrated, these bulky species get in each other's way, decreasing the mobility of the charges. So initially, the conductivity of the solution rises linearly as you increase the ion concentration. But then the rate decreases as ion mobility starts to decrease, because conductivity is the product of concentration and mobility. That's why the graph appears asymptotic.
Did you make any interesting observations during the experiment? You might have noticed tiny bubbles coming off one of the electrodes, and if you were using copper wire, you might have noticed the solution take on a green or teal tint by the end of the experiment. What's going on? Well, chemistry is going on. At one electrode, copper atoms on the surface of the electrode are giving up electrons to form Cu+ ions. These ions dissolve into the water, giving it a greenish hue. You can see that in this clip. The electrons then go racing off down the wire to the positive side of the battery. This is the associated half reaction. At the other electrode, water molecules are breaking up and the hydrogen atoms are coming off as protons. The protons pick up electrons delivered to the electrode from the negative side of the battery to form neutral hydrogen atoms, which then combine to form H2 molecules, which coalesce into bubbles of hydrogen gas. This is the associated half reaction. Now there's an entertaining way to confirm that these bubbles are hydrogen, because hydrogen is highly combustible, so if we collect some and expose it to flame, it should burn explosively. To do this, you'll need something to collect the hydrogen in. A test tube works great. You could also try a small pill bottle. You'll also need a low voltage power supply. A spare electronics charger that you don't mind partially destroying will work well. To collect the bubbles, you'll need to replace one of the electrodes on your cup with a partially insulated wire that's bent in such a way that you can put your small vial over top of the uninsulated portion. Next, take your vial and fully submerge it in your cup so that it's full of water. Then, without letting any of the water out of the vial, invert it and place it over the free end of your new electrode. Then connect your power supply to the two electrodes, sit back and wait. Your vial will slowly rise up to the surface as it fills up with hydrogen gas. This does take about 10 minutes, so you do have to be patient. Now this last part you'll want to do rather quickly, so make sure you watch through the whole thing before you try it yourself. Have someone light a match and then carefully place your finger over the vial and lift it out of the water, doing your best to make sure that no hydrogen escapes. Then remove your finger and have your partner quickly try to push the match into the vial. The hydrogen gas will catch fire, as you can see here, and it should make a little pop noise. If you made it this far, thanks so much for watching, and we hope you learned something and had fun.